All right, welcome. Today we are going to tackle a really fun computer science puzzle. The question is this: how do you take a string of letters and slice it up so that every single piece is a palindrome? Let's dive right in.
So, picture this. I hand you a string of letters. How many different ways can you chop it up so that every single chunk reads the same forwards and backwards? It sounds simple, right? But it leads to a surprisingly elegant solution. Okay, first things first, let's make sure we're all on the same page. A palindrome is just a string that's the same forwards and backwards, like race car or level. And for what we're doing today, it's super important to remember that even a single letter, like B, or a simple pair, like AA, they totally count. These are going to be our building blocks.
Okay, so here's the twist. The real puzzle isn't just finding one way to chop up the string. Nope, our goal is to find every single valid way to do it. And that, right there, is where things get interesting.
So let's look at a super simple example to make this crystal clear. If you have the string ABA, one perfectly valid solution is to just slice it into individual letters. A, and B. They're all palindromes? But you could also group those first two A's together to make AA. That's a palindrome too. So AAB is another valid solution. We need to find both.
So that's the real question, right? How do we build a system, an algorithm, that can methodically check every single possibility and not miss a single one? We can't just wing it. We need a solid strategy.
And the perfect tool for this job? It's Recursion. Recursion is just fantastic for problems like this, where you can break a big problem down into smaller versions of the exact same problem. Let's see what that really means. And this quote right here, it just hits the nail on the head. Think about it. Once we make our first palindromic cut on our string, what are we left with? Well, we have a smaller string that needs the exact same process run on it. It's the same job, just on a smaller piece of the puzzle.
A great way to think about this is to imagine our function is a detective. It's investigating the string. It finds the first valid clue, a palindrome. Then, for the rest of the string, the rest of the mystery, it calls in a new detective to do the exact same job on that smaller piece.
All right, theory time is over. Let's put our detective on the case with a slightly trickier string, AABB. This is where you're really going to see this whole approach come to life.
So, our detective looks at AAB. The first move? Let's try slicing off just the first A. Is A a palindrome? Yep, it sure is. Okay, we'll add that to our path. And now we call in a new detective to solve the rest of the mystery, ABB. Okay, so that first detective passed off AB to a new one. What does this new detective do? The exact same thing. It slices off the A, checks it, and then passes the rest, B, to a third detective. That last detective can split B into B and B. We've hit the end of the string, and boom, we found our first full solution, A, B, B. But, and this is a big but, we are not done, not even close. And this right here brings us to the absolute magic ingredient of this whole process, backtracking. Once a detective finds a solution, it doesn't just clock out. It reports its findings, and then it goes back, it undoes its last decision, and it checks to see if there was another road it could have taken. This is how we find all the answers. So remember that last detective looking at B? It backtracks. It undoes its last move. Instead of splitting it into B and B, it says, wait a minute, what if I take the whole thing? Is BB a palindrome? Yes. So now we have a second complete solution, AABB. See how that works?
Okay, now for the really cool part. We're going to backtrack all the way to the beginning. Our original detective, the one who first looked at AAB, is back on the case. It says, okay, that whole path starting with A is done. What if instead my first move was to take AA? Is AA a palindrome? Yes! It then hands off the remaining BB to a new detective. And since we already know there are two ways to solve BB, this one move instantly finds our last two solutions.
And just like that, look at what we've got. By systematically exploring every possible first move and then backtracking to try the next one, our detectives have uncovered all four possible ways to partition ABB. No guesswork involved, just a perfect, repeatable system.
Okay, so we've walked through it, we've seen the detective work in action. Now let's boil this all down into a clear, step-by-step blueprint that you could actually code up.
Here's the whole strategy laid out. You've got a base case. If you're at the end of the string, congratulations, you found a solution. Otherwise, you loop through all the possible cuts you can make. If a cut gives you a palindrome, you add it to your current path, and you call yourself, the recursive call, on the rest of the string. But that last step, the backtrack step, that is the absolute key to the whole thing. After a detective finishes its job, it removes its clue from the path. That's what allows us to go back and explore all the other options.
So at this point, you might be thinking, all right, that's a cool little puzzle for slicing up strings, but why should I really care? Well, let me tell you, this pattern is so much bigger than just this one problem. This whole idea of explore a path and then backtrack if it doesn't work out, it's a fundamental pattern in computer science. It's the go-to strategy for any problem where you have to search through a giant sea of possibilities to find all the answers, not just the first one you happen to bump into.
I mean, think about it. Finding your way through a maze. You go down one path, you hit a dead end, you backtrack, you try another. That's the same logic. Or solving a Sudoku puzzle. You put a number in a square. See if it works. If it leads to a contradiction, you backtrack, erase it, and try a different number. This very same pattern powers game AIs, logistics planning, and so much more. So the next time you're staring down a problem that just has a dizzying number of potential solutions, I want you to remember our detective. Remember this pattern. Make a choice, follow it through, but always be ready to backtrack and try a different path. It's an incredibly powerful way to find order in chaos. So my question to you is, what complex problem are you going to solve with it?